These are the answers to the AP Chemistry packet on topics 7.6 to 7.10. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. In question 1, it says, based on the information above, the value of Kp for equation number 2 is closest to, and then we have 4 numerical choices. So this question falls under topic 7.6, properties of the equilibrium constant. And one of the essential knowledge statements says that when a reaction is reversed, the equilibrium constant K for the reversed equation is equal to the reciprocal of the original value of K. So if we take chemical equation number 1 from the table that we're given, which has a value of Kp equal to 0.16, and we simply reverse that equation, now the new value of K for the reversed equation would be 1 divided by 0.16, and that works out to be 6.25. Now that's not our final answer to question 1 because we still have to deal with the coefficients. So right now, the coefficients in that reversed version of equation number 1, the coefficients are 1, 1, and 2. And as you can see in the table above, the coefficients for chemical equation number 2 are actually 1/2, 1/2, and 1. So another essential knowledge statement in topic 7.6 says that when the stoichiometric coefficients of a reaction are multiplied by a factor n, then the equilibrium constant K for the modified equation is equal to the original value of K raised to the power n. So if we take the equation that has an equilibrium constant of 6.25 and we multiply each of the coefficients by 1/2, so that now the coefficients are 1/2, 1/2, and 1, then the new value of K would be 6.25 raised to the 1/2 power. So the square root of 6.25 would be the correct answer to this question, and that is 2.5. Just to summarize, the original chemical equation number 1 has been both reversed and multiplied by 1/2. So the equilibrium constant for equation number 2 is equal to 1 divided by 0.16 raised to the 1/2 power. And if we do that math, we get a value of 2.5. So again, the correct answer to question 1 is choice B. Now, let's take a look at question 2. Question 2 in this packet is very similar to question number 1. It says, based on the information above, the value of Kc for equation number 3 is closest to, and then we have 4 numerical choices. So question number 2 in this packet also falls under topic 7.6, properties of the equilibrium constant. And one of the essential knowledge statements says that when reactions are added together, the equilibrium constant K of the resulting overall reaction is the product of the individual K values for the reactions that were added together. So here we have equation number 3, and we need to determine how equations number 1 and 2 can be combined together to equal equation number 3. So I'm going to start with the first substance I see as a reactant in equation number 3, and that is PbF2 solid. And I need 1 mole of PbF2 to be on the left side of the equation. But since in equation number 1, that's exactly what appears. There's 1 mole of solid PbF2 on the left. That means that no change needs to be made to equation number 1. I'm going to go ahead and just rewrite equation number 1 exactly as is with no modification to the equation or the value of K. But now when I look at the substance aqueous HF, which appears on the right side of equation number 3, I need 2 moles of HF to appear on the right side of the equation. And with equation number 2, there's only 1 mole of HF, and it's actually on the left side of the equation. So that tells me that equation number 2 needs to be both reversed to get the HF on the other side of the equation, and also multiplied by 2 to get a coefficient of 2. So now I'm going to write the modified version of equation number 2, which has been both reversed and doubled. And the equilibrium constant for this modified equation will be 1 divided by 6.8 times 10 to the negative 4, and then also squared. Again, I have to reverse the equation, so the new k would be the reciprocal, and then multiplying by 2 means that the k value is raised to the second power. So when I do that math of 1 divided by 6.8 times 10 to the negative 4 squared, I get a value of 2.16 times 10 to the 6th power. Now all I have left to do to produce equation number 3 is to add these two equations together. And when I add these two equations together, the F minus, or the fluoride ion, is going to get crossed off on both sides of the equation, and I end up with equation number 3. Now, the equilibrium constant for equation number 3 would be the product of 3.6 times 10 to the negative 8 and 2.16 times 10 to the 6. So I need to multiply these two k values together to get the correct answer to question 2 in this packet. So when I do that math, I get 7.8 times 10 to the negative 2, and that means that the correct answer to question 2 is choice D. Now let's take a look at question 3. In question 3, it says a 0.10 mole sample of each of the 4 species in the reaction represented above is injected into a rigid, previously evacuated 1-liter container. And the question asks, which of the following species will have the highest concentration when the system reaches equilibrium? Now, this question falls under topic 7.3 because we have to compare the reaction quotient Q and the equilibrium constant K. And then this also falls under topic 7.7, calculating equilibrium concentrations. So the strategy for answering question 3 is to create a rice table. So let's go ahead and create a rice table so we can fill in the initial amount of each of the substances that was present at the beginning of this experiment. So we are told that a 0.10 mole sample of each of the 4 species was added. So I'm going to go ahead and fill in 0.10 mole for each of the 4 substances. And then I will remember that concentration is moles divided by the total volume in liters. So because we have a 1-liter container, then 0.10 mole per liter means that each of these numbers, 0.10, is actually not only the number of moles, but also the concentration, or the number of moles per liter. Now I'm going to go ahead and set up the expression for the reaction quotient Q. And that's going to be products over reactants. So it's going to be the concentration of CS2 times the concentration of H2 raised to the 4th power, because there's a coefficient of 4, divided by the concentration of H2S squared, again because there's a coefficient of 2, and then also on the bottom is the concentration of CH4. And so now, in order to calculate the numerical value of the reaction quotient Q, I'm going to plug in the initial concentration of each substance, which is 0.10 moles per liter. Now, when I do this math, which would be 0.1 times 0.1 raised to the 4th power, and then divided by 0.1 squared, and then also divided by 0.1, I get 0.01 for the value of the reaction quotient Q. I need to compare the value of Q with the value of K. And we were given in this problem that the value of Kc is equal to 3.4 times 10 to the negative 4. But we've just determined that the value of the reaction quotient Qc is equal to 0.01. So now we know that Q, or Qc, is greater than K. So if Q is greater than K, then what's going to happen is there's going to be a net conversion of products to reactants, or from right to left, until equilibrium is achieved. So now that we know that Q is greater than K, there will be a net conversion from right to left or from products to reactants, I'm going to fill in the change row of my rice table, remembering that the change will always be in proportion to the coefficients in the balanced equation. And since my coefficients from left to right are 2, 1, 1, and 4, that means that the magnitude of change in terms of x will be 2x, x, x, and 4x. But since there's going to be a net conversion from products to reactants or from right to left, I have plus 2x, plus x, and then minus x, and minus 4x. Again, because there's going to be a net conversion from products to reactants in order to reach equilibrium. Now, at equilibrium, the concentration of each substance from left to right in this table will be 0.1 plus 2x, 0.1 plus x, 0.1 minus x, and then 0.1 minus 4x. And now that we've filled in the final row of the rice table, we can officially answer question 3. So the question says, which of the following species will have the highest concentration when the system reaches equilibrium? I'm going to go ahead and eliminate choices C and D because the concentration of those substances will be less than 0.1 molar. So the correct answer to this question is going to be which substance has the highest concentration at equilibrium, and since 0.1 plus 2x should be a greater value than 0.1 plus x, that means that the correct answer to question 3 is choice A. Now let's take a look at question 4. In question 4, it says at 450 degrees Celsius, 2.0 moles each of hydrogen, iodine, and hydrogen iodide are combined in a 1 liter rigid container. And the question asks which of the following will occur as the system moves toward equilibrium as represented by the equation above. So the strategy for answering question 4 is very similar to the strategy that was used to answer question 3 in this packet. We need to compare the value of the reaction quotient Q with the value of the equilibrium constant K. So let's set up the expression for the reaction quotient Q. It's going to be products over reactants, and that would be the concentration of hydrogen iodide squared, because we have a coefficient of 2 for HI, divided by the concentration of hydrogen, and then also divided by the concentration of iodine. Now, the initial concentration of each substance would be 2 moles per liter, because we have 2 moles of each substance in a total volume of 1 liter. So when I plug in the concentration of 2 moles per liter for each substance, then the math would be 2 squared divided by the product of 2 times 2. So now I know that the value of the reaction quotient Q is going to be 1. And we were given in this problem that the value of the equilibrium constant, Kc, is equal to 51. So if I have a Q of 1 and I have a value of K of 51, that means that Q is less than K. So what does it mean when Q is less than K? What that means is that if Q is less than K, then we'll have a net conversion from left to right, or from reactants to products, until equilibrium is achieved. So if there's going to be a net conversion from left to right, or from reactants to products, then let's go ahead and eliminate some of the choices here in question 4. I'll start by eliminating choice A because it says Q is greater than K, and that's incorrect. And I'm also going to eliminate choice D, which says no net reaction will occur because the number of molecules is the same on both sides of the equation. So there is going to be a net conversion from left to right, or from reactants to products. So both choices B and C indicate that Q is less than K, but in choice C, it says the total pressure in the container will decrease. And if we look closely at the details of this balanced equation, we can see that each side of this equation has a total of 2 moles of gaseous substances. Therefore, the total number of moles of gas and the total pressure in the container should remain constant as the system reaches equilibrium. So we're not going to see a change in the total pressure, so I can eliminate choice C. So the correct answer to question 4 is choice B. More hydrogen iodide, which is a product, will be produced because Q is less than K. Now let's take a look at question 5. In question 5, it says a mixture of the substances X2, Y2, and XY is placed in a previously evacuated rigid container and allowed to reach equilibrium at a constant temperature as shown above. And the question asks, which of the following sets of initial concentrations would lead to the formation of more XY3 as the system moves toward equilibrium? So we're looking for a set of conditions in which the additional product will be formed. And since XY3 happens to be a product, we're looking for a situation in which there will be a net conversion from reactants to products or from left to right. So that means as we examine the value of Q and compare the value of Q with the value of K, we're looking for the correct answer in which Q is less than K, because that would lead to the formation of additional product, or XY3. So let's write the expression for the reaction quotient. It's going to be products over reactants. So in this particular chemical equation, that will be the concentration of XY3 squared, because there's a coefficient of 2. And then on the bottom would be the concentration of X2, and also on the bottom would be the concentration of Y2 cubed, because we have a coefficient of 3. So I'll start with choice A. Let's plug in these 3 values for the initial concentration, and we'll see if Q is less than or greater than K. So when I plug in these values, it's going to be 2 squared, and then divided by the product of 0.5 times 1.5 cubed. Now, when I do that math on my calculator, I get a value of 2.4 for the reaction quotient. I have to compare the value of Q with the value of K. But the value of K is 0.4. So that means that with choice A, Q is greater than K. That would lead to a net conversion from right to left, or from products to reactants, and that's not what we're looking for, so we can go ahead and eliminate choice A. Now, moving on to choice B, it would be 4 squared divided by the product of 0.5 times 1.5 cubed, but this also results in a value in which Q, 9.5, is greater than K, which is 0.4. So again, I can eliminate choice B. We're looking for a situation in which Q is less than K. When I take a look at the numbers for choice C, it's going to be 2 squared divided by the product of 1 times 3 cubed. And when I do this math on my calculator, I get 0.15. Now, this is exactly the situation that we're looking for. Now Q is less than K. So choice C is going to be the correct answer here in question 5, but let's go ahead and just confirm that. So when I check the data for choice D, it's going to be 4 squared divided by the product of 1 times 3 cubed, and this math leads to a value of 0.59, which again is greater than K. So again, the correct answer for question 5 is choice C. We're looking for a net conversion from left to right, or from reactants to products, and the reason why choice C is the correct answer is because it's the only choice in which Q is less than K. Now, let's take a look at question 6. In question 6, it says, substance A2 reacts with substance Q2 to produce substance AQ2 according to the equation above. And the question asks, which of the following particulate diagrams is the best representation of the reaction mixture after equilibrium has been achieved at 500 Kelvin? Assume that each molecule in the diagram represents 1 atmosphere of gas pressure. So question 6 falls under topic 7.8, representations of equilibrium. And the essential knowledge statement says that particulate representations can be used to describe the relative numbers of reactant and product particles. So let's go ahead and take a look at particle diagram A, and then we'll analyze how many particles of each substance are present in each of these four diagrams. So with diagram A, I can see 2 particles of A2, which are represented by the white circles. I see 4 particles of Q2 represented by the black circles, and then I also see 4 particles of substance AQ2. Now I'm going to write the expression for the reaction quotient Q for this chemical equation. So it's going to be products over reactants, and we're going to use partial pressure because this is a QP, not a QC. So it's going to be the partial pressure of substance AQ2 on top, and that's going to be squared because there's a coefficient of 2. And on the bottom, we have the partial pressure of the reactants. So partial pressure of A2, and then also on the bottom is the partial pressure of Q2, and that is squared because there's a coefficient of 2. So when I plug in these values for the diagram, particle diagram A, it's going to be, assuming that each molecule represents 1 atmosphere, partial pressure of AQ2 would be 4. And on the bottom, it's going to be partial pressure of A2, which is 2, and also on the bottom, partial pressure of Q2, which is 4. So when I do this math of 4 squared divided by the product of 2 times 4 squared, I get 0.5 on my calculator. Now, the value of Kp is given to us in this question as 0.125. And the question says, which of the following particulate diagrams is the best representation of the reaction mixture after equilibrium has been achieved? So what we're looking for is a situation in which Q equals K. We're looking for 0.125 as the correct answer for question 6 in this packet. So I can already say that I can eliminate choice A because the value of Q, or the reaction quotient, is 0.5, and it's supposed to be 0.125 for the system at equilibrium. Now let's move on to particulate diagram B. So when I count the particles, I can see 4 particles of each substance, and then the math involved would be 4 squared divided by the product of 4 times 4 squared. So when I do that math, I get 0.25, so I can now eliminate choice B. I'm looking for a value in which Q equals K. I'm looking for 0.125 as the correct answer. So moving on to particle diagram C, when I count the particles, I have 2 particles of A2, 4 particles of Q2, and 2 particles of AQ2. So I'll substitute into the reaction quotient, and it's going to be 2 squared divided by the product of 2 times 4 squared. And when I do this math, I now have determined that choice C is the correct answer because Q for that particular diagram is equal to 0.125. Now, just to confirm that D is not the correct answer, when you count the particles, we have 4 particles of A2, 4 particles of Q2, and 2 particles of AQ2. And when we plug in those numbers into the expression for the reaction quotient, it would be 2 squared divided by the product of 4 times 4 squared. And that gives us 0.0625, which is not the correct answer. So again, the correct answer to question 6 is choice C, because when we use the information in the particulate diagram for choice C and we plug it into the reaction quotient expression, we get a value of 0.125, indicating that that particulate diagram is the best representation of the reaction mixture at equilibrium. Now let's take a look at question 7. In question 7, it says, which of the following changes will increase the amount of carbon dioxide, or CO2, in the equilibrium system represented by the equation above? Now, question 7, as well as actually all of the questions that remain in this packet, so questions 7 through 12 in this packet, they fall under topics 7.9 and 7.10, which has to do with Le Chatelier's principle. So Le Chatelier's principle can be used to predict the response of a system to stresses, such as addition or removal of a chemical species, change in temperature, change in volume or pressure of a gas-phase system, or dilution of a reaction system. Now, let's take a look at question 7, and I'm going to focus initially on choices C and D, because in choices C and D, it talks about changing the volume of the reaction vessel. And in my video where I covered Le Chatelier's principle, one of the things I mentioned about gases is the following. I said that changes in the volume of the reaction vessel can cause a disturbance in a gaseous equilibrium system, but only when there are different numbers of moles of gas on opposite sides of the chemical equation. And as we consider the chemical equation here in question 7, we can see that each side of this chemical equation has a total of 2 moles of gaseous substances. Therefore, changing the volume of the reaction vessel will have no effect on the position of this equilibrium system. So we can go ahead and eliminate choices C and D in question 7. So now it comes down to either removing hydrogen from the system, which happens to be a product, or removing water from the system, and water happens to be a reactant. So in my video for Le Chatelier's principle, I'd presented a summary of different situations, and so I'll highlight that if some of the reactant is removed, then Q becomes greater than K, and the system shifts toward the left or toward the reactants. But if some of the product is removed, then Q becomes less than K, and the system shifts toward the right, toward the products. And so because in question 7 it said, which of the following changes will increase the amount of CO2, removing some of the hydrogen, which happens to be a product, from the system will cause the value of Q to become less than K. And this causes the equilibrium system to shift toward the right, toward the products, and this would increase the amount of CO2. So the correct answer to question 7 is choice A, removing hydrogen from the system. Now let's take a look at question 8. In question 8 it says, the reactions represented above are carried out in sealed, rigid containers and allowed to reach equilibrium. If the volume of each container is reduced from 1 liter to 0.5 liters at constant temperature, for which of the reactions will the amount of products be increased? So in terms of Le Chatelier's principle, when we have a situation in which the volume of the reaction vessel is decreased, then what will happen for a gaseous equilibrium system is that the partial pressures of all of the gaseous species increase when the volume of the reaction vessel is decreased. And the system shifts toward the side of the equation that has a lower number of moles of gaseous particles. So in question 8, we're looking for a shift toward the right side of the equation in order for the amount of the products to be increased. So that would mean that the correct chemical equation that we're looking for in question 8 is the one in which there are fewer moles of gaseous substances on the right side of the equation. Now let's go ahead and take a look at the difference for reactions A, B, C, and D. So the chemical equation for reaction A, there's 2 moles of gas on each side, so we can eliminate choice A. And with choices B, C, and D, for reaction B, the chemical equation has 4 moles of gas on the left, 2 moles of gas on the right. For the chemical equation for reaction C, there's 2 moles of gas on the left, 3 moles of gas on the right. And for the chemical equation for reaction D, we see 1 mole of gas on the left, 2 moles of gas on the right. So now we can see that the correct answer to question 8 is choice B, because it's the only one in which we have fewer moles of the gaseous substances on the right side of the equation. So when the volume of the container is reduced, then there will be a shift toward that side of the equation that has fewer moles of gas, which would be the right side or the product side of the equation. So correct answer to question 8 is choice B. Now let's take a look at question 9. In question 9, it says, a pure sample of PCl5 is placed in a previously evacuated 2-liter reaction vessel. When the system has reached equilibrium at 500 Kelvin, according to the equation represented above, the total pressure of the reaction mixture is equal to 1.5 atmospheres. Then, the volume of the reaction vessel is reduced from 2 liters to 1 liter, and equilibrium is reestablished for the reaction system at 500 Kelvin. At this point, the total pressure in the reaction vessel should be, and we are given 4 choices, less than 1.5 atmospheres, greater than 1.5 but less than 3 atmospheres, equal to 3 atmospheres, or greater than 3 atmospheres. So what I'm going to do to help us understand what's going on in question 9 is to remind you of a question that I had presented, a similar question from my video that covers Le Chatelier's principle. So here on this slide was the question that I had presented in that earlier video. We can see that there is a chemical equation involving N2O4 and NO2. And there's 1 mole of gas on the left, and there's 2 moles of gas on the right in this chemical equation. But as you can see highlighted on this slide, the volume of the reaction vessel is decreased from 2 liters to 1 liter. So what happened is at that moment, the partial pressure of each gas was doubled, and that caused the total pressure of the reaction mixture to be doubled. And then what happened next is that the equilibrium was reestablished by shifting toward the side of the equation with fewer moles of gas. And so that happened to be from right to left. And so as a result, when equilibrium was reestablished, the total pressure was slightly less than the pressure at the moment of the change. So to summarize on this slide, what happened is that we had a total pressure of 4.77 plus 1 for the 2 gases. That would be 5.77 atmospheres. But at the moment that the volume of the reaction vessel had decreased from 2 liters to 1 liter, at that moment the total pressure was doubled from 5.77 atmospheres to 11.54 atmospheres. But then when equilibrium was reestablished, where there was a shift toward the side of the equation with fewer moles of gas, the total pressure was slightly less than 11.54 atmospheres. Now let's go back to question 9. It's a similar situation here in question 9 in that we have a system that's at equilibrium, and then the volume of the reaction vessel is reduced from 2 liters to 1 liter. So at that moment, the total pressure would be doubled from 1.5 atmospheres to 3 atmospheres. But then equilibrium will be reestablished, and there'll be a shift toward the side of the equation with fewer moles of gas. And so when equilibrium is reestablished, the total pressure in the reaction vessel will be slightly less than 3 atmospheres. So the correct answer to question 9 is choice B, that when the system has reestablished equilibrium, then the total pressure in the reaction vessel would be greater than 1.5 atmospheres, but less than 3 atmospheres. Now let's take a look at question 10. In question 10, it says, the synthesis of CH3OH, which is methanol, from CO, or carbon monoxide, and hydrogen, is represented by the equation above. And the value of the equilibrium constant, Kc, for the reaction at 483 Kelvin is 14.5. And the question asks, when the temperature of the system is increased to 650 Kelvin, which of the following identifies what happens to the value of Kc and provides the correct justification? So we can see in the 4 choices here listed for question 10 that we have to decide if the value of Kc will decrease, or increase, and then choose the correct justification. So in my video for Le Chatelier's principle, I talked about the different scenarios, that what happens when temperature increases or decreases for a reaction. So here are the four possibilities. If the temperature of the system is increased and the reaction happens to be endothermic, then there will be a shift from left to right, from reactants to products, and the value of K increases. Now, if the temperature is increased, but the reaction is exothermic, then there will be a shift from right to left, or from products to reactants, and the value of K decreases. Now, there's also two more possibilities. If the temperature of the system is decreased, then for an endothermic reaction, there will be a shift from products to reactants, or from right to left, and the value of K decreases. And if the temperature is decreased, for an exothermic reaction, there will be a shift from left to right, or from reactants to products, and K increases. Now, let's go back and take a look at the details here in question 10. Now, for the justification here in question 10, 2 of the 4 choices indicate that the reaction is exothermic. And we can see next to this balanced chemical equation, it says that the sign of delta H is negative, that the delta H is less than 0. So when the delta H is negative, then the reaction is exothermic. But the other 2 justifications talk about how the activation energy of either the reverse reaction or the forward reaction is decreased. Now I'm going to remind you of something that I had presented back in Unit 5, which is on kinetics. This is topic 5.11, catalysis, that in the presence of a suitable catalyst, then there can be a new reaction path with a lower activation energy. But here, in question 10, there's no mention of the use of a catalyst, so we have no reason to believe that the activation energy of either the reverse or the forward reaction would be affected by simply increasing the temperature from 483 Kelvin to 650 Kelvin. So the activation energy should not be affected, which is why I'm going to go ahead and eliminate choices B and D. And again, we know that the reaction is exothermic because the sign of delta H is negative, that delta H is less than 0. So I'll remind you of what I had presented a few moments ago, and that is that when the temperature of the system is increased and the reaction is exothermic, then there will be a shift from right to left, or from products to reactants, and as a result, the value of K decreases. So now we can see that the correct answer to question 10 is choice A, that when the temperature of the system for this exothermic reaction is increased, there will be a shift from right to left, or from products to reactants, and the value of K will decrease because this reaction is classified as exothermic. So correct answer to question 10 is choice A. Now let's take a look at question 11. In question 11, it says a mixture of N2O4 gas and NO2 gas is placed in a container and allowed to reach equilibrium according to the equation shown above. The amount of NO2 gas present in the reaction mixture at equilibrium can be maximized by, and we can see 4 choices involving a change in temperature and involving a change in the volume of the container. So let's start with the temperature. The delta H for this particular reaction is positive. The delta H is greater than 0. So what that means is that the reaction is classified as endothermic. When we have a positive delta H, the reaction is classified as endothermic. And as I had mentioned in my explanation for the answer to question 10 of this packet, here's how an increase in temperature will affect the equilibrium position for an endothermic reaction. So when the temperature of the system is increased, there'll be a shift from left to right or from reactants to products if the reaction is classified as endothermic. That means that the correct answer to question 11 is going to be increasing the temperature. So the choice would be either A or B. I'm going to eliminate C and D because it says decreasing the temperature. Now let's take a look at the difference between the left side of the equation and the right side of the equation in terms of the number of moles of gas. So for this equation, we see 1 mole of gas on the left and 2 moles of gas on the right. And we're trying to maximize the amount of NO2, so we'd like there to be a shift toward the side of the equation that has more moles of gas, which happens to be the right side of the equation. Now, when the volume of a reaction vessel is increased, then what happens when you increase the volume of a reaction vessel is that the partial pressures of all gaseous species decrease. And as a result, the system will shift toward the side of the equation that has a higher number of moles of gaseous particles. So to answer this question, we'd like to increase the volume of the reaction vessel because that would cause a shift toward the right side of the equation, which happens to have more moles of gas. So the correct answer to question 11 is choice B. Increasing the temperature for an endothermic reaction will cause a shift toward the right side of the equation or toward the products. And then in this example, because there's a greater number of moles of gas on the right side of the equation, then increasing the volume of the container will also cause a shift toward the right side. So again, correct answer to question 11 is choice B. Now let's take a look at question 12. In question 12, it says, which of the following changes will increase the amount of CO2, or carbon dioxide, in the reaction system at equilibrium represented above? Now on this next slide, I'm presenting something that I had presented in my video for Le Chatelier's principle. And so what you can see on this slide are examples of a stress imposed on the equilibrium system and then how the equilibrium system responds to the stress. So the first thing that's highlighted is a catalyst is added to speed up the reaction. So what happens is that no shift in the equilibrium system will occur, but the system will simply reach equilibrium at a faster rate if a catalyst is added. What's also highlighted on this slide is that what happens when additional solid is added or some of the solid is removed. No shift in the equilibrium position will occur because when a solid is added or removed, then the concentrations or the partial pressures of all species remain unchanged. So solids are not included in the equilibrium constant expression, and so adding additional solid or removing some of the solid will not cause a shift in the equilibrium position. And then one more example that's highlighted on this slide is that when an inert or an unreactive gas, such as helium or neon, is added to a gaseous equilibrium system, there is no shift that would occur because the partial pressures of all of the reacting gaseous species remain unchanged. So the additional presence of some unreactive gas does not cause any shift in the equilibrium position. Now let's go back and take a look at the choices for question 12. So choice A, adding a suitable catalyst. All that will do is cause the system to reach equilibrium more quickly, but it will not cause an increase in the amount of carbon dioxide. So we can eliminate choice A. Choice B says removing a small amount of solid carbon. Again, removing a small amount of a solid will not cause a shift in the equilibrium position, so we can eliminate choice B. And then increasing the pressure by adding an inert or an unreactive gas, such as helium or neon, will not cause a shift. So it looks like the correct answer to question 12 would be choice D. So choice D says decreasing the volume of the reaction vessel at constant temperature. And we can see that on the left side of this equation, there's 2 moles of gas. And on the right side of this equation, we have 1 mole of solid and we have 1 mole of gas. So there is a difference in the number of moles of gas. So to kind of show you why choice D is the correct answer, if the volume of a reaction vessel is decreased for a gaseous equilibrium system, then the partial pressures of all gaseous species increase as a result of decreasing the volume of the reaction vessel. And the system will shift toward whichever side of the equation has a lower number of moles of gaseous particles. So in this example, that would be toward the right side of the equation, which has only 1 mole of gas, and that would result in an increase in the amount of CO2 for that particular system. So the answer to question 12 is choice D, decreasing the volume of the reaction vessel. Now, question 12 represents the last question in this packet. I hope that you found all of these answers and explanations helpful. Thanks for watching.